we'll now visit the campus distribution node, which services as an aggregation point for surrounding buildings. You can see the fiber coming into this node through conduits that are installed on its outer wall. Each of those smaller black cables contains tens to hundreds of individual fiber strands. As with the IDFs and BDFs, these strands are terminated on fiber patch panels, and patch cords are used to connect them to the network equipment in the node. Each rack you see here houses fiber from a few dozen surrounding buildings. Since the distribution node serves many buildings, a failure at this node can affect network connectivity for users in all these buildings. It therefore makes economic sense to provide a high level of redundancy at this node. Accordingly, this node has redundant distribution layer devices. At USF, these are Cisco 6500s and Cisco Nexus 7000s. They are a combination of a switch and a router. They route traffic between different subnets and switch that traffic out to the surrounding buildings. The fiber optic cables you see plugged into these devices connect to the building distribution switches that we just saw in the BDF. They typically run a few thousand meters underground from that BDF to this distribution layer device. Looking again at the simplified network diagram, you see that each distribution layer device is uplinked to both core devices. These uplinks run at speeds between 10 gigabits per second and 100 gigabits per second, depending on the bandwidth demands of a particular node. These links also use the same single-mode fiber that we use from the buildings to the distribution nodes. All devices we use at USF's distribution layer have redundant power supplies and, where possible, redundant forwarding hardware. The node itself has a dedicated generator, and UPS capable of running the room for at least 4 hours in the event of a power failure, including if the generator doesn't start, and sufficient redundant cooling to keep the room at around 72 degrees even if all but one of the air conditioning units fail. From the distribution layer, we move up into the campus core. The Tampa campus backbone is made up of 2 redundant Cisco Nexus 7000 devices. In fact, the core equipment is basically identical to the distribution layer equipment. The core equipment simply aggregates distribution layer devices like the distribution layer aggregates buildings. Looking back at the more detailed network diagram, you can see how the 2 core devices connect together each of the distribution layer devices, and you can see the path that we've been following from the desktop up to the core. This path is replicated for the tens of thousands of devices connecting to USF's network. But the design is fairly simple. Desktop wiring closets aggregate to the building wiring closet. Buildings aggregate to distribution nodes, and the distribution nodes are networked together by the core devices. At this point, you might be asking yourself how the routers in USF's distribution and core layers figure out where to forward the traffic they receive. This routing decision is accomplished by building a table of reachable networks and where traffic should be forwarded next to reach those networks. This table is built automatically using a routing protocol called OSPF, or Open Shortest Path First. This protocol is run by all of the routers in USF's network. It defines how those routers should exchange network reachability information, and it tells those routers how they should build their routing table so that they have a loop-free best path route to all networks. For example, here is a route to the network 10.220.60.0/22. As you can see, the routing protocol tells us that this network is reachable via the next hop of 131.247.254.34. We have hundreds of these routes in our network.